Hello, let us now discuss in this video the different types of biasing that we normally use in common emitter BJT amplifier circuit designs. So the first you can see on screen there are two circuits which has been written. The one circuit is we do biasing by fixing the base emitter voltage. We also do biasing by fixing the base current. Okay, so this is the first circuit and this is the second circuit. Now let me go with fixing VB. I'll try to write a series of equations which makes me to think how biasing, what makes this biasing can be considered. Okay, so here, when I say it is fixing VB, now which is VB? The voltage across, this is the base, if you see here. This is my emitter and this is my collector. Now if you see this voltage, which is base emitter voltage. Okay. So if I say from base till ground is VB, and as we don't have any resistor which is connected to the emitter here, I can say that the voltage VB and voltage VB, if you see voltage VB here, this is the voltage, base voltage at the base terminal. This is base emitter voltage between base and emitter. Now when I say base voltage, it is voltage from the base terminal to ground. So I can say voltage across RB2, the resistor RB2 is VB. If I say voltage across base and emitter, voltage across base and emitter, voltage across base and emitter is actually VBE. If you try to see in the circuit properly, try to see the circuit and let me tell you what it is. Can I say that the base voltage what you see here, VB, which is the voltage between base and ground, is also voltage between base and emitter, because see base and emitter from base till ground can also be base and emitter voltage. So in this case I can say that your VB and VB both are equal. VB and VB are both equal. Okay, so in this biasing circuit what we did is we have connected RB1 and RB2, which is considered as voltage divider. I can say this is voltage divider because whatever the voltage VCC is given at this particular point will be divided based on these two resistors, and that divided voltage is what you can see, which is VB. When the VB is getting reduced, or VB voltage is getting divided because of these two resistors connected in parallel, which is in turn connected to the base terminal. Okay, so therefore if I take this is VCC, your RB1 is connected here, this is my VB base voltage, and this is my RB2 which is connected here. Now when I say VCC is from this terminal to ground. VCC is from this terminal to ground, is your VCC. When I say VB, it is voltage from this terminal to ground, is my VB. So this part of the circuit I can apply voltage division rule. And through voltage division rule I can define the equation for VB. Now what is VB is, equal to total voltage VCC. I am applying voltage division rule. Keep that in mind. Voltage division rule, when we have two different resistors in series, in all series circuit, voltage gets divided. In all parallel circuits, the current gets divided. So this simple phenomena, you people know it already. So therefore, as RB1 and RB2 are in series, and I need to find out what is the voltage across RB2. Okay, what is the voltage across RB2? So therefore, voltage across RB2 is VB. So therefore, VB equals, by using voltage division rule, VB equals total voltage VCC multiplied by the same resistance where the voltage is been need to be find. So that is RB2 divided by RB1 plus RB1 plus RB2. Now this is my VB, equation for VB. Okay. Now, but unfortunately in this circuit, we also know that VB and VBE are equal, right? VB and VBE are equal. What is VBE? That is very important now. Very important thing which I am going to tell you now. Now we know that the voltage VB is voltage across base and emitter. Base and emitter, right? And I told you in the previous video that the transistor is made up of two diodes. One is the collector diode and another one is the emitter diode. Now you will have a emitter diode here. Okay, the diode will be here, emitter diode. Whereas the collector diode will be somewhere like this, like here. Okay. So as we have an emitter diode, the voltage across this terminal of an emitter diode is actually between base and emitter, and this is actually VBE. And whatever the transistor that we are going to take is a silicon, okay, silicon based. So once we know it is silicon based, the cutoff voltage of any silicon diode, we know the cutoff voltage of any silicon diode, voltage of silicon diode is equal to 0.7 volts, is equal to 0.7 volts. Therefore, by looking into this diagram, you can easily say that your VBE is equal to the cutoff voltage of the diode, which is 0.7 volts. So therefore, through this we can say your VB is equal to 0.7 volts, because VB was equal to VB, which we have written here. So VB equals 0.7 volts. So this is how you are fixing the value of VB. Okay, you are fixing the value of VB. Now let us look into the equation of IB. Let us look into the equation of IB. IB equals what? Okay. So to find out IB, what we need to do is we need to go with this law. Like, let me tell you. Now to find out IB, we need to go with this law. This loop we need to consider. Okay. Now this we know this is VB. So when I look into this law, I can easily say that my IB, okay, IB equals, voltage, the current flowing through to the base terminal, okay, is equal to voltage across this and voltage across this. So you are going to take the difference among those voltages and divided by the resistance connected to the base, which is RB2. So I can say IB equals VB minus VBE divided by RB2. VB minus VBE divided by RB2 is what I can say the equation for IB. Whereas after finding out the IB through this equation, we know that IC equals beta times IB. This equation is what we have derived. We can see in some basic discussion on transistors, where IC is equal to beta times IB, where beta is the current gain. So once IB is being found through this equation, it is easy to find out what is IC through this equation. And earlier I told you that our IE equals IB plus IC, and I also told you it is approximately equal to IC because IB is very small value. IB will be very small. So I can approximately IE to equal to IC. Okay. So in this equation you can find out what is IE also. Now coming to the equation of VCE, because for Q point, I already told you for Q point there are two values which is very much necessary. One is IC and another one is VCE. Okay. Now I will go back to the circuit to write the equation for VCE now. Okay, let me write the equation for VCE by looking into the circuit. So if I want to write the equation for VCE, I am going to take this loop. What is that loop here is this loop from year to year, this loop. So I'll just write it separately here. This is RC. You have a transistor, emitter connected to ground, and this is your VCC, right? And this is your, now if I say properly, if I mark the voltages, VCC is from here to ground is your VCC. Okay, this is your VCC. Now if I say this one, which is collector voltage VC, and if I say from here, this is the emitter voltage V. Okay. Now, my job is to know what is VCE. I need to know what is the voltage VCE. I need to know what is voltage VCE. Now, the voltage across, now if you look into this, circuit, this is the voltage VC. And if I say what is voltage across collector and emitter, okay, if I ask you what is voltage across collector and emitter, can I say our VCE and VC are equal? VC and VCE are equal. Why? Because emitter is directly connected to ground. There is no any emitter resistor there. Therefore, if I measure voltage from collector to ground, it is as good as measuring voltage between collector and emitter. Therefore, I can easily say that the collector and emitter voltage are, the voltage across collector and emitter is equal to the voltage at the collector point what we measure. Now, if I say what is VC, you have an RC here. Okay, you have an RC here where the current IC is flowing here. Okay, so that is very important for you to know here. Okay, now when I say voltage across from year to year is actually your ICRC. ICRC. And if you look into this old diagram, can I say that your VC or VCE equals total voltage from year to year is your VCC minus, say from year to year is A, from year to year it is B, and from year to year is C. Can I say my B equals total voltage A minus C? So that is what I am doing here. My B is nothing but VC equals VC, and that is equal to total voltage which is A, which is VCC, minus the part C, which is ICRC. ICRC. Now this is the equation that we use to find what is VC. Now with these two equations, okay, with this VC and with this IB, and due to IB, we can easily find out what is IC. So this will give me the Q point values IC and VCE. This is the 2 points which we can see in Q. in the DC load line. Now, this is one type of biasing which is being done to make VCE and IC to be completely dependent on the base voltage or the base resistance, or if you see VCE, it is completely dependent on RC. Okay, whereas VCC and IC is what we generate through the circuit, where RC is one which is external resistance which we are going to connect. See, this biasing is done like that. When I say biasing, RB1, RB2, RB1, RB2, and this RC, it is all your job to connect. It is the external resistance which we are connecting to the transistor to create biasing. Okay, so that is the benefit of biasing. You are going to connect some external resistors so that you are able to generate the equations for VC and IC, where you are having complete freedom to maintain the Q point because of connecting these external resistors. Okay, students, let us now discuss about fixing IB. Now, when I say fixing IB, this is the circuit which we are going to discuss now. And this is the way the circuit is connected here. Now you don't see RB1 and RB2, you don't see voltage divider biasing circuit here. You have removed one RB2 so that now the IB is completely fixed. Now if I say the equation for this, it is very simple now. IB will definitely be equal to, you need not to find out VB, because in this circuit you can easily say that VB is nothing but VB only. Okay, so therefore my IB will be equal to your VCC. The other end of the circuit is VBE. VBE divided by the base resistor RB. So this is the formula. Earlier, when we had this circuit, we were able to see the equation was VB minus VBE by RB2. But in this equation, as there is no voltage dividing which is happening at this particular base point, I can easily say that one end of the voltage is VCC, the other end of the voltage is your VBE. So VCC minus VBE divided by RB will be equal to your current IB. Okay, so that is what the equation for IB that is been written. Very simple. Now, through this IB, you can easily find out what is IC, because we know IC equals beta times IB. Now, to find out VC, now this part of the circuit in this particular, biasing circuit, whereas this part of the circuit in this biasing circuit is one and the same. Can you see here? They both are same. So therefore, VC or VCE, which are both are equal, and the equation remains to be same, which is VCC minus IC RC. So these two values will now give me will now give me the value at Q point. This is how IC and VCE are been obtained in a BJT biasing by fixing the base current IB.